Thanks, Amin. My name is Florian Torno, and I'd briefly like to talk about two Activate-related aspects that happened over the past year. As this picture suggests, cold air outbreak have strong cloud transitions from overcast to broken, and so much of our research has been driven by the question of why that is and what facilitates that. The first item of these two I want to present is a paper that just got accepted in the Journal of Atmospheric Sciences, where we looked into exactly these cloud transitions, and we're puzzled by a pre-campaign case. So this is a case from 2008, scrutinized already in another paper from 2 years ago. But here we were puzzled by why is it that further to the north, clouds tend to have a shorter overcast period compared to regions further to the south. And similar to presentations, I've already drawn trajectories through here that I'm going to use in a moment. But first I'm going to wonder, is this a stationary, is this a snapshot perspective from the polar orbiting satellite actually what's happening in geostationary in a more Lagrangian fashion if we follow this air mass? And it turns out it is. So here we take successive geostationary imagery, and by applying thresholds to either brightness temperatures or visible reflectances, we can detect that also here trajectories further north show shorter overcast periods. Now, we hypothesize that dry intrusions might drive this pattern in cloud transitions, and this is something that appears pretty much in every extratropical cyclone. So we have these different conveyor belts, and then you see here the postfrontal sector where most of these cold air outbreaks appear. And this dry intrusion is an air mass that comes from high above and then sort of penetrates as free tropospheric air, subsiding just above the cold air outbreak. And so what we're suggesting here is that a gradient in meteorology might drive this gradient in cloud transitions. So for example, looking into reanalysis data that we followed along these trajectories, we found that further north, so close around 0.2 here, that's illustrated on the right, we have reduced subsidence. We also have greater free tropospheric humidity. In addition to being closer to the low pressure system, there's greater wind speed around here, and also being further north, there's lower boundary layer temperature. Now, looking into other research, for example, from subtropical stratocumulus clouds, each of these ingredients should make for a lower cloud fraction or less cloud amount. And that's indeed also what we found here when applying Lagrangian LES along 4 selected trajectories. I already showed this in these pictures here. So we have 4 trajectories that kind of span the sector. And fairly similar to previous work, we initialize with reanalysis data and then nudge to reanalysis data above the boundary layer. So the boundary layer itself is free running, and then above the boundary layer, we nudge to the prevalent conditions from reanalysis data. And what we find, I can explain the sketch, is that where there's less subsidence, the cloud deck is allowed to deepen more compared to regions where there's more subsidence. And that happens while the cloud base itself stays relatively steady, despite strong surface fluxes that introduce heat and moisture, and despite strong entrainment that introduce heat and relatively little moisture. So where the cloud deck is allowed to deepen, we get thicker clouds with more liquid water pass. At the same time, we train air that's relatively clean compared to the boundary layer. We know that thanks to Activate's data over the past couple of years. And so paired together, we have a thicker cloud with less and less droplets. So rain initiates sooner in these clouds, and that makes also for a sooner transition compared to trajectories further south. We can look at that also in a more quantitative manner. Here, these 4 trajectories are shown by column, and then different observational targets from polar orbiting satellites are shown as rows, as, for example, cloud top temperature, cloud cover, optical thickness, liquid water pass, droplet number, and surface precipitation. And what you see is these 2 left columns that's further south indeed show a slightly longer extent of the overcast period compared to these 2 on the right. So the grayish background shows the overcast period. And we indeed see that the liquid water ramps up. So these dots, these crosses here show MAC liquid water pass that has a steeper slope in these 2 northern trajectories compared to further south. And likewise, we see a steeper decline of droplet number concentration. Now, one thing I'm not showing here is also what Pekita just motivated. There's a lot of ice in these clouds, and we didn't find any good observational constraints for ice. And that brings me to my second point. What happens in a warmer world? Will cold air outbreaks with less ice amplify a warming or counteract it? So that brings me to a brief report from a breakout group that that Gregory, Sazana, and myself led at the joint CF-MIP gas meeting in Paris this year, where we aim to extract a cold air outbreak cloud feedback. And we want to do that as follows. We want to use Activate here in the Northwest Atlantic as the warmer future climate. And then cold air outbreaks from Comble, that's were sampled here in the Norwegian Sea as the colder past. Now, these two campaigns are fundamentally different. As we know, Activate had 2 aircraft, while Comble lacked these, but instead had ground stations that were sort of favorably situated up and downwind of these cold air outbreaks. Nevertheless, we can take roughly a handful of cases from each of these campaigns and see that there's some dissimilarities. For example, SST is crucially different between the two. However, if we look at an MCO index as a function of fetch here, these two compare actually quite well. And so situated in this joint meeting, we came up with this approach, like a 2-pronged approach, where on the left, we sort of cater to the gas community, which I learned is more a process-oriented community. So they're more interested in very dedicated observational cases that can be then brought to the LES space, and from there to the single color model that informs on the parent system models processes. And we can cater to the CF-MIP community, where we take AMIP and AMIP plus 4K simulations, and from these extract regions, and from these regions extract conditions that are favorable for cold air outbreaks, for example, through weather states or wind direction. And then through both prongs arrive at a set of cases that range in cloud top temperature, and then thereby help to extract a cloud feedback component. Now, Gregory Sazana has done some preliminary work taking the right prong and shows, for example, that there's, I don't think he filtered for cold air outbreaks, just for regions. Anyway, that there's large responses in cloud fraction in the high altitudes, but concentrating on the lower altitudes, for example, there's a response such that liquid clouds tend to have less cloud fraction with increasing temperature. And we also want to learn, for example, for this left prong that I'm showing here, from the ongoing efforts that are led for Comble at the moment, where there's a web-based platform that provides model sort of initial and boundary conditions that can be used for participants, that they then download, run their large eddy simulation or their single column model, upload these results, and are able to compare against other people's work and observational targets similar to what I showed in the previous point. And that's all I have. Thank you.
So you mentioned ARM here. I know that Combo is part of ARM program. Is this model comparison also sponsored by DOE ARM or?
Yes, so they provide the resources to host the data and also to have a toolbox, a Jupyter Hub platform where people can sort of use Python environments to work, to compare data and plot it and apply sort of satellite, sort of instrument forward simulators and so forth. So there's a whole range of tools that are ready for participants.
Participants can also upload their model results directly to the ARM data discovery, or?
Yeah, I'm just showing this inspiration for how we want to conduct this this 2-pronged effort. But in this specific example, participants can upload their model results. Yeah.
Okay, thanks.
Okay, well.